Bonjour, mes amis. Previously, we talked about scalars, vectors, and SI units. Today, we're going to be building upon that knowledge by finding ways to describe motion. So, I want to start off this lesson by talking about a pretty important concept known as the center of mass. Now, for the purposes of most of this course, we will be viewing objects undergoing motion as a single mass located at a single point. This simplifies many complications that might come with a complex body or object. For example, let's say we were observing a sprinter that was running around a track and it was moving in this direction. We know that just from observing that the sprinter's arms would move much quicker or have a higher speed than the actual body itself. So to make matters a little less complicated, we approximate the entire body as a single point, where the single point is located at the body's center of mass. Now, the center of mass is a location on a given geometry determined by the distribution of mass on that geometry. For example, the center of mass for a circle would be right in the middle, as the mass would be distributed evenly around the shape. For an equilateral triangle, however, the center of mass would be located further down, as a majority of the mass would be distributed in this half of the geometry. For now, this is as in-depth as we need to go to tackle most of the problems throughout this course. So now that we know that we can describe a body as a single point of mass, how do we actually go about describing motion? Well, there are parameters that describe an object's motion, which we'll go through right now. The first being displacement. Now, displacement is a vector that describes how far and in which direction the object has moved with respect to its starting point. And this is not to be confused with distance, which is purely a scalar quantity. For example, if an object traveled 15 meters east, then 3 meters west, its displacement from its original point is only 15 minus 3, which is 12 meters to the east. Whereas the distance would be equal to 15 plus 3. So we'd have a total distance traveled of 18 meters. So the key thing here to remember is that displacement is measured in relation to a specified point, whereas distance is the total length that is traveled. So let's go ahead and move on to our second quantity that we look at when we're describing motion, and that quantity is velocity. Velocity, just like displacement, is also a vector, and it describes how quick a body is traveling with respect to some direction, where we can calculate the average velocity of an object by dividing the displacement an object experiences over the time or the period of time that we're measuring, where the symbol for displacement is also x and time is t. So we can say v is equal to x on t. And this is not to be confused with the concept of speed, which only describes how fast an object is traveling, and it doesn't pay attention or doesn't take into consideration the direction in which the object is traveling. So the equation for speed, which we denote with s, is equal to distance over time, which is why displacement is denoted in x and distance is denoted with a d, so that there's no confusion between distance and displacement. So let's go back to our example above, where we were talking about the difference between distance and displacement. We saw that the distance that this object, we'll call this object A, covered in a period of, let's say, 5 seconds, was 18 meters, and the displacement was 12 meters. So if we were to measure the velocity, or work out the velocity, we would get 12 divided by 5, which would give us 2.4 meters per second. Remember, time is measured in seconds, and x, or displacement, is measured in meters, whereas our speed would be equal to 18 divided by 5, which would give us 3.6 meters per second. Now, the direction associated with the velocity would be east, and that's because, as we can see from this diagram, for a majority of this object's movement, the movement would be towards the east. So the overall velocity would also be towards the east, whereas speed would just be the total distance divided by the time, and we wouldn't be concerned with the direction this object was traveling in. So let's look at our final quantity that we're going to be considering when we're describing motion, and that is acceleration. And acceleration is just the change in velocity over a certain time period that we specify. Now you'll notice here that I've written a little triangle. What does this triangle mean? Well, the triangle denotes something pretty important in physics, which is called delta, or change. It's the difference between the final state minus the initial state. So in effect, acceleration, which is the change in velocity over time, is equal to the final velocity minus the initial velocity divided by the time period that we're concerned with. For example, say we had a car that was initially traveling at 20 meters per second to the east. And let's say we put our foot on the pedal so that the car eventually had a velocity of 30 meters per second. And let's say this took about 10 seconds to occur. So our final velocity would be 30 meters east. Our initial velocity would be 20 meters east. So we can plug that in, and our time would be 10 seconds. So we could plug these values in to find the acceleration, to say 30 minus 20 divided by 10, which gives us an acceleration of 1 meters per second divided by seconds, which is 1 meters per second squared. Now if we go back to our SI units lesson, we learnt that physical quantities can be expressed as a combination between mass, length, and time. So for acceleration, we have a velocity, which is a change in length over a change in time, where length is measured in meters and time is measured in seconds, and acceleration is just a change in velocity over time. So the dimensions become meters divided by seconds once again, to give us meters per second squared. Let's have a look at one final example before we close out this lesson. Let's say we have a ball, and we throw this ball right at a wall. So we got a giant wall here, we got a ball. And let's say this ball is initially traveling with a speed of 4 meters per second, and it's going towards the right, so the speed is 4 meters per second, but the velocity is 4 meters per second east, or to the right. And let's say once this ball hits this wall and comes back at us, the speed it returns with is 3 meters per second, and the velocity it comes back with is also 3 meters per second, but it's towards the west now, or it's in the opposite direction, so we'll say left or west. And suppose we want to find out two things. We want to find out the change in speed, and we also want to know the change in velocity. And let's also add in one more, layer of complexity to this. And let's say this interaction here occurs over the space of let's say 0.5 seconds or 50 milliseconds. Now the change in speed is just equal to the final speed minus the initial speed. And because we're not concerned about the direction when we're talking about speed, because speed is obviously a scalar, we can just go ahead and plug in the magnitudes. So we can say 4 minus 3 equals 1 meter per second change. What about our change in velocity? Well, that's a little bit more involved. From our equation, we see that the formula for the change in velocity is equal to Vf minus Vi, which is the same as saying the final velocity minus the initial velocity. And because now we're dealing with velocities, which are vectors, we need to find a mathematical expression for the directions in which these balls are traveling in, or which this ball is traveling in, rather. We can take the right as positive, which would make the left negative. So then this velocity here, which is our initial velocity, would be 4 meters per second positive. And this velocity here, which is our final velocity, will be negative 3 meters per second. Which we can then go ahead and plug into our change in velocity equation over here to say V final, which is negative 3, minus 4 is equal to negative 7 meters per second. And because we've got this negative out here, all this is telling us is that the change in velocity occurs in the left direction. So we can rewrite this to say the change in velocity is equal to 7 meters per second left. So let's move on to our final bit of this question and find out what the acceleration is. Well, we know acceleration, which is also a vector, is equal to the change in velocity divided by the change in time. We know the change in velocity is negative 7, where the negative indicates left. And we know the time over which this change occurs, the change in velocity occurs, is 50 milliseconds, which is 50 times 10 to the negative 3 seconds. And we know velocity is measured in meters per second. Then the acceleration becomes 140 meters per second squared towards the left, because this negative would have stayed there, but I've just taken that negative out and said towards the left. I've just realized I've made a little silly mistake over here, and I've said time is equal to half a second. What I meant to say is time is actually equal to 0.05 seconds, which converts to 50 milliseconds. And that brings us to the close of this lesson. Thank you for joining me for this one. I hope it was helpful, and I'll catch you at the next one.